is the portion of the spectrum that has the proper length, that between 400 to 700, that stimulate optic nerve. And I did mention this earlier, the human eye perceives the wavelengths from 400 to 700 millimicrons.
Anybody have any questions?
The shorter waves, 400 millimicrons, produce the colors of blue, the blue end of the spectrum, and the longer waves, 700 millimicrons, produce the colors of the red end of the spectrum. So that's your red end and your blue end. Red, orange, yellow, green, blue, indigo, violet. As we all learned, or many of us learned this in the elementary school, so RGB, the acronym for the color range. So we can demonstrate this by taking white light and passing it through a prism, and the colors will break into the various components. So that was Newton's finding.
AKA rainbow.
AKA rainbow, yes. So as I indicated, the visible part of the electronic spectrum is made up of these colors. If you take white light and you pass it through, it's going to break into its component parts. And I'll have this presentation where if at the end of the seminar, if you're interested in having it, I can see it here.
So basically, everybody's aware of the additive color theory, where you take red, blue, and green and produces white light.
Equal values of red, green, and blue will produce white light. Just as white light passed through a prism can break into red, green, and blue, and everything in between. Roy J. Biv, orange, yellow, green, blue, indigo, violet. Okay, we can demonstrate that here in our good friend Photoshop. Red, green, and blue is a color system known as the additive color system because it adds the different wavelengths to create light. So if and it starts off with no light. So here's a scene where there's no light, complete darkness. If I were to, let's look at my channels. Your channels will be where your red, green, and blue will be shown. So you can see it here, red, green, and blue, and with no light, it's all dark. If I were to make a selection here, and I go to my red, and I'm going to put some light on my red, and display red, green, and blue. As you can see, that's light at 100 at its brightest point. 255. Light can be from 0 to 255. 0 being no light to 255 is brightest point. Okay, so this is pure white. So that's light at its brightest point, and it's showing. I put the color on the red channel, so I'm seeing red. If I were to go to my green, Right now, my green channel is completely black. If I were to transmit 100% light into that same area in the green, yellow light. So red, 100% red light, 100% green light coming together will create yellow. At this point, blue light is being blocked out. As you can see, there's no blue light. Solid black. We're seeing yellow because green light is reflecting and blue is green is reflecting, excuse me, red and green are reflecting, blocking out blue, so we're seeing the color yellow. When we add equal brightness of light in blue, and I turn on all my channels, red, green, and blue viewed together, we have white. So equal values of red, green, and blue will create white light. Equal values of red, green, and blue, let me restate that. Equal values of red, green, and blue at its brightest point will create white light. If I use varying degrees of each one of them, I can create all the colors in the rainbow or in the spectrum. So a 5% instead of 100, 100, 100, or 255, 255, 255, as I just showed, if I went 10, 50, and 255, it will show a different color. If I go 250, 20, and 40, because I'm projecting different levels of brightness in each channel, it will show me different colors as I project these colors.
And that's in the transmissive color form. He's talking strictly transmissive.
Yes. And it's and of course, is the additive, color. I'm not talking where you can take a crayon and color red and color blue and color green and get white. No, we're talking light. We're talking light, not pigment at this point. There's no pigment at all. When I take red light, green light, white light in equal values of 100% of it, or 255 level, the brightest point, that's what I'm going to get. If it's half of it, 128, 128, 128, I get gray. Equal values will always create a neutral color. When one of the colors shift and it's not equal, you get something different. You can mismatch those colors in various strengths or brightness to obtain just about every color in the spectrum. Okay.
I was going to add on to what you were saying as far as the various degrees of how the colors might have different light or percentages, which we create hue. That's going to be your hue, where it's going to either be on a warmer side or colder side of that particular color, based on the fact that they're not at equal measurement or values. So that's, I'm kind of jumping the gun, but that's pretty much the definition of hue.
Okay. So additive color is what we just looked at, the additive color process, red, green, and blue, okay, allowing us to add various colors to create whatever color we want to see. And we've indicated that if we create the brightest point in each color zone, 255, 255, 255, we end up with white. If we were to do 10, 10, and 10, that would be a gray color.
Actually,
However, if
that'd be black.
yeah, it will be
Black.
black, but there is some level of transmission going through, but you're going to see it as black. Complete black will be 0, 0, 0, 0, 0, where there's absolutely no transmission of light.
Right.
Okay. Although at 10, 10, 10 on your screen, you're going to see black. But if you had a way to project light through something that's made up of 10, 10, 10, there is a certain level of that will allow light to transmit through it. However, at 0, 0, 0, there's absolutely no light that will transmit through it because it's all blocked out. Okay.
That is correct, because 10 would be like a 95, 90-ish, if you were to relate that percentage.
Yeah, and at 95%, it looks black. If you have a 95% black, value, it will look black, right? So the eye will perceive it as black. But that means there's 5% chance that something can go through it. If I print a 95% black on paper, there's 5% of the color of the paper coming through. I may not be able to see it, but it's there. Okay.
Any questions up to this point?
Okay, so the we just talked about the additive process. So if I see somebody wearing red, for instance, what does that mean? I see someone wearing red. I can see there's a red shirt. What does that mean? How am I seeing that color? It's because I see red because the other two colors have been filtered out. Red is projecting itself while blocking out green and blue, which is what you just saw here. If I go in here, this is 100% red. It's kind of hard to yeah, until if I block out, let me see, let me block this out for a second. And then I'll do the same in the green. Okay, so as you can see, my green is completely black. My blue is completely black. What has light in it? The whiteness, the brightness, is red, right? So that's why we're seeing that. Well, we're seeing red because it says, I'm blocking out everybody else. Green and blue, you're out of the scene. I'm going to project myself. Well, the same thing happens with this car right there. We're seeing what we're seeing because the red in there is acting as a filter and blocking out green and blue and allowing itself, to show. Okay? So the question is everything red, green, and blue? No, you have everything in between, right? Well, if you have everything in between, then as I demonstrated, red and green will create what? Yellow. A little bit of red, a little bit of green will create some kind of yellow, but not yellow at its fullest strength. Right? So with different combinations of these colors, we can just about create everything that we're wearing right here. That's how we see what we see. Who is projecting itself? How much of that is being projected? Who is being blocked out? Is it completely being blocked or is it partially being blocked? That's how we see in the additive color system. We don't print in using the additive color system, however. We print using the subtractive color system. Cyan, magenta, yellow. We don't count that black as a color. We only use it to boost the inks. These colors should combine at 100% together to give us black. But because of their own innate deficiencies, they're deficient in the sense that it's man-made and it doesn't really do everything that it's supposed to do. So they fall short of the three combining to give you that solid black.